Hi friends, this is the second video for the directional derivative of functions of serial variables. We have seen in the first video the directional derivative for the scalar fields where we have the function from Rn to R. Now in this video we shall study the directional derivative of functions from Rn to Rm, which we usually call as the vector fields. So for this we take S to be a subset of Rn and A an interior point of S. If we suppose we have the function f from S to Rm as any vector field defined on S and y is a point of Rn, we define the derivative f dash of ay is equal to limit h tend to 0 a plus hy minus f of a over h whenever the limit exists. If this limit exists, then we call this quantity f dash of ay as the directional derivative of the vector field at a point A, directional derivative of f at a point A in the direction of vector y. And it's understood that this f dash of ay is a point of Rm because you have actually the difference range of f actually is contained in Rm. So there's a point of Rm, there's a point of Rm, difference is a point of Rm, and this is h is here a scalar quantity. You are multiplying to each component of this vector by h. Finally this will be a point of Rm. We call this f dash of ay as a directional derivative of vector field at a point A in the direction of vector y. Now if we have explicit expression for this f as a function of n variables which is whose range falls in Rm, that's if we have f of the form, if f is equal to f1, f2, so on, fm, because it's actually the function from Rn to Rm, so its range will be the points of Rm, be the points of space Rm. Then we define the f dash of ay. In this case, the directional derivative is defined to be the directional derivative of each component. So we take the directional derivative component wise, f dash 1 ay, f dash 2 ay, then dash f dash m ay. So this is the directional derivative in case you have f of the form. Since you know this is a point of Rm and Rm is a vector space, we can choose the basis of Rm. Since I can take E1, E2, so on, Em as a basis of, as a standard basis of, as a basis of Rm, so I can write f dash of ay equal to, you know, when this is a base of Rm, every point of Rm can be expressed as a linear combination of these. Since this is a point of Rm, I can write this as f1 dash ay of E1 plus f dash 2 ay E2 plus so on plus f m dash ay em, which implies f dash of ay is equal to summation k run from 1 to m f dash k of ay of E1. So this is the expression for the directional derivative of vector field. We can write this directional derivative component wise. Okay, this is the expression for the directional derivative of vector field f at A in the direction of y. Now we have seen in the last video the relation between the directional derivative of a differentiable function, but that was for the scalar field, when f was a scalar field. That in that video we saw when f is a scalar field, the total derivative and the directional derivative at a point are equal. Total derivative at a point is equal to the directional derivative at that point in every direction. So that result was for the scalar field. Now in this video we shall see that the same holds for the vector fields also. If we have a differentiable vector field, then the directional derivative at every point, at a point, then the directional derivative at a point at which the function is differentiable is exactly equal to the directional derivative, the total derivative at that point. This we will see in this result. This one says us if f from S continued in Rn to Rm is differentiable at an interior point A in S. So this is a vector field here because it's from Rn to Rm. The range is in Rm, so it's a vector field. This is differentiable at S, exactly the way we discussed it in the last video. It is differentiable at A, where A is interior point of S, and its total derivative is here given to be TA, with total derivative at A, TA. So TA is the total derivative at A. You know this TA is here the linear transformation from Rn to Rm. Then the directional derivative f dash of ay exists at A in every direction y in Rn. So t of A is exactly equal to f dash of ay for every y in Rn. So this is exactly the same relation, but now this time you have the vector field on the right side. Further, if you have f exactly equal to this f1, f2, so on up to f of m, in this case this is a vector here in Rm. In the last video this was simply here the real valued function. This f was a real valued function, but now f is a m tuple of real valued function. Each of these, f1 is a real valued function of n variables, f2 is a real valued function of n variables, and so on. Fm is a real valued function of n variables, and y is this vector. Then I can write t of a equal to k run from 1 to m delta of fk a dot y into ek, where ek is the kth basis element. This is also equal to this. This we have to show. This also equals to this one. So this actually connects the total derivative at A with the directional derivative at A in the direction y. The proof of this is exactly the same as the proof of scalar field. So the scalar field and the vector field, they have almost the same proof. No need to repeat here, but I want to see this very interesting relation between total derivative at A and this very vector notation. For this you can see. So I will omit the proof of this one, TA and f dash of ay. This is exactly the same. Of course, this is here TA of y. TA of y. TA of y is f dash of ay for every y in Rn. Let me see the proof of the second part. I can call this as the part first and this as part second. Proof of part second. Since t of ay as proved in part first, t of ay is equal to f dash of ay, but you can see f dash of ay, f is this m tuple, so you can say this is f1 dash ay, f2 dash ay, so on, fm dash ay, because you can give it component wise. but then you can write this as f1 dash of ay. You know, this is here a real number, because you are evaluating this at a in the direction of y. In the direction of y, this is a real number, this is a real number, all these will be the real numbers for given y. This will be, this I can write as f dash 1 ay plus f2 dash ay e2 plus so on plus fm dash ay of am, because you can write every vector as a linear combination where I am choosing e1, e2, so on, em as a standard basis for rm. So this is summation k varying from 1 to m fk dash of ay into ek. Then this is summation k varying from 1 to m. You know, in the vector, in the scalar field, we have proved there, when we have some f was there, some function from Rn to Rm, Rn to R. This differentiable function there, that was already given to us, differentiable function there. That time we saw f dash of a y, when you have a real valued function, this is equal to delta of f a dot y. If you will see the video once again, the last video once again, there you will see if f is a differentiable function from Rn to R, then first of all, that very relation ta of y is equal to f dash of ay. That relation holds first of all, and after that we deduced this relation there, f dash of a y is equal to delta of f a dot y. These are equal. Now f is there, the real valued function. Here you can see each of these fi's. Suppose f1 dash ay, this is a real valued function, this is a real valued function. Each are differentiable because the whole f is given to be the differentiable function. This f is differentiable means each of these components are differentiable, means this is differentiable. So I can apply this result. Whenever I have f dash of ay, I have delta f a of y dot y. So I can write f dash ay delta f a y. But I have here, I have such m functions, each is real valued. So you will have the notation k for individual function. First function you have 1, second function you have 2, and so on. So this function will have the value then delta of fk a dot y into ek. Now I can expand this f dash of ay equal to delta of f1 a dot y e1. Expand this sum, you have m terms here, these m terms, but this combination can be written as dot y comma delta f2a dot y dash dash delta fma dot y. How this follows actually? You have delta f1a dot y, delta f1a, you know delta f1 actually, what delta f1 is, or generally I will write delta of f at a in general. This is actually del by del x1, or you can say del f by del x1 at a, del f a by del x2, so on. Del f by del xn at a. This is actually the meaning of this very delta. So this is this f1 is first of all itself a function of n variables. When you evaluate this, you have a vector here. So this is vector, y is vector, this is m vector because function is of n variables. So this is here n vector. Y also belongs to Rn. Y is n vector, so this will be a scalar here. This is a scalar here. This is a scalar here. That's why actually you were multiplying to this even by a scalar quantity, by a scalar quantity, by a scalar quantity. So when you expand this, you have the first component this, others are 0 plus. So you have m vector here. First component is 1. This delta of f1a dot y, other is 0. Similarly, this has second component this has mth component this. When we add, you get this. So this finally implies f dash of ay has this vector notation delta f1a dot y delta f2a dot y so on delta fm a dot y. So this is the formula.